Hi guys. So in this video, I am going to present the proof for the nested interval theorem. So this video and the next couple of videos will in fact serve as lemmas for a different proof that I want to present. So that is the proof of the Bolzano-Weierstrass theorem. And there are a few different lemmas that we need to prove before we can prove that theorem. And this is the first of those lemmas. Now, the primary reason why we need to, prove the Bolzano-Weierstrass theorem, at least, for the purposes of these series of videos, is to prove the theorem that every continuous function that maps from a compact set is uniformly continuous on that set. So I want to use the Bolzano-Weierstrass theorem to write a proof for that theorem. But to prove the Bolzano-Weierstrass theorem itself, I need to prove a couple of lemmas. And this is the first lemma. And this is, of course, the nested interval theorem. So let's quickly go over the statement of the theorem, and then we'll write a proof for it. So the theorem says let I1 be equal to the closed interval a1 b1 and I2 be equal to the closed interval a2 b2 and so on. So essentially what I'm saying is ik is the interval, the closed interval of ak comma bk. So this is in general what the kth interval will look like. So what I'm saying is let this be a sequence of closed and bounded intervals in R. So of course they are closed and they are also bounded. Suppose that each one of these, so suppose that I1 is a superset of I2, which is a superset of I3, and so on. So in other words, what this essentially means is that I2 is completely contained in I1, I3 is completely contained in I2, and so on. So if I were to draw this on a number line, on a number line, what this would essentially look like is as follows. Let's say that this is A1 and this is B1, then A2 will lie somewhere over here and B2 will lie somewhere over here. So essentially what this means is that given that these intervals are well defined, I1 lies inside I2 lies inside I1, and then I3 lies inside I2, I4 lies inside I3, and so on. And that's basically the concept that is described by this relationship, that I1 is a superset of I2 and so on. Okay, so that's the first condition. That's the first assumption that we're making. So each of these intervals is contained in another interval. And the second assumption that we're making is that the length of ik, or in other words, bk minus ak, tends to 0 as k approaches infinity. So in other words, as we start to write out I3, I4, and then as i's of k, as k tends to infinity, the length of the interval becomes 0. So in other words, what's happening is that if this is A1 and this is B1, then after a long time, let's say this is AK and BK, well, what's happening is that a's of k and b's of k are moving towards each other, or in other words, the difference between b's of k and a's of k is going towards 0, which essentially means that the length of the interval i's of k is going to 0. So the length of the sequence of intervals is becoming smaller and smaller as k tends to infinity. Okay. So given these two assumptions, given that each one of these intervals is contained in some other interval, and the assumption that the length of the intervals is tending to 0 as k approaches infinity, the theorem says that there is exactly one point that is contained in all of the sets, in all of the intervals i's of k. So in other words, the union of all the intervals is just a single point. So in other words, this final condition can also be described like this. The intersection from k equals 1 to infinity of i's of k is one point, and let's say that that point is L. So that's just the point L. So that's just the set containing the point L, and that is what we need to prove. So the first recommendation that I will give you in order or in terms of approaching this theorem is to actually draw a number line and first convince yourself that this theorem is true. Once you've done that, you will probably be able to write a proof for this theorem. The proof is not that complicated, it is quite elementary. Um, and it's also quite intuitive. If you start drawing out stuff on a number line, you'll pretty much quite quickly convince yourself that the theorem is true. So, yep, pause the videos and see if you can solve this question on your own. So, I hope you've attempted this question on your own. So, yep, let's go ahead and write a proof for this theorem now. So, the first thing you need to recognize is you need to use both conditions. So, both conditions A and condition B needs to be used in order for you to to prove this theorem. This theorem does not hold if property A is true but property B is false, and it doesn't hold if property B is true and property A is false. Both of these properties need to be true. Okay, so given that, let's begin. Note that the condition I1 is a superset of I2, which is a superset of I3, and so on, essentially means that ace of 1 is less than or equal to ace of 2, which is less than or equal to ace of 3, and so on, and base of 1 is greater than or equal to base of 2, which is greater than or equal to base of 3, and so on. So just to quickly elaborate upon why this is true, this should be quite trivial. Even if you draw a number line, let's say this is A1 and this is B1, then if you draw, and of course this is just I1, so this is the first interval. Now if you want to draw any interval that lies inside I1, you need to pick a starting point that is greater than A1 and an ending point that is less than B1. So while or less than or equal to or greater than or equal to. So in this case, for example, let's say this is the point that I pick as A2 and this is the point that I pick as my B2. Clearly B1 is greater than B2 and A1 is less than A2. And you can continue this process inductively for I2, I3, and so on. So basically, this condition will hold, the condition that I've just described above. This means that both sequences that are both ace of k, the sequence ace of k and the sequence b's of k are monotonic sequences. Of course, ace of 1 is an increasing sequence and b's of 1 is a decreasing sequence. Sorry, b's of k is a decreasing sequence and ace of k is an increasing sequence. So that's the first thing, they are both monotonic. Additionally, both ace of k and b's of k are bounded sequences. In particular, for all k in the set of natural numbers, the sequence ace of k, while ace of 1 is less than or equal to ace of k, which is less than or equal to b's of 1. This is the first thing, and in fact, you know what? I'm just going to write it out this way. Both b's of k and ace of k are contained inside ace of 1 and b's of 1, or they're sandwiched between ace of 1 and b's of 1. And this once again should be true. Once again, if you and it should also be quite trivial. If you draw out the interval I of 1, then you should quickly realize that every other interval lies inside this interval. So the interval, the kth interval, ak comma bk, will also lie inside this interval. So let's say this is ace of k and this is b's of k. So in particular, I mean, the trivial bounds for the sequences ace of k and b's of k are just ace of 1 and b's of 1. The I mean, the sequence ace of k will never be greater than b of b1, and then the sequence b's of 1 will never be less than ace of 1, or sorry, the sequence b's of k will never be less than ace of 1. So these both these sequences are bounded as well. Thus, by the monotone convergence theorem, so MCT, okay, so the monotone convergence theorem, and this theorem essentially states that if a sequence is monotonic and bounded, then it's convergent. By this monotone convergence theorem, as ace of k and b's of k are monotonic and bounded, both sequences must converge. Okay, so now we know that both sequences ace of k and b's of k converge. The next thing we need to do is to figure out exactly what value they converge to. So for the purposes of this proof, the more pertinent question, or the more important question, is whether or not both sequences, that is ace of k and b's of k, converge to the same value. So notice that as k tends to infinity, b's of k minus ace of k tends to 0. That is, both ace of k and b's of k have the same limit. So why does this imply that both ace of k and b's of k have the same limit? Because the idea is that if you pick a case sufficiently large enough, then the difference between ace of k and b's of k is negligible. It is 0. So therefore, both sequences ace of k and b's of k must converge to the same value, or to the same limit. So I'm going to say let capital L be this limit. Okay. Then, as the sequence ace of k is an increasing sequence, well, that is what we have already established. Ace of k is an increasing sequence. Or I guess increasing is not the correct word. Maybe we should be using the word non-decreasing, because, well, it can also be, well, I mean, each subsequent term is less than or equal to the previous term. So increasing is not the correct terminology, maybe. So maybe we should, use the word non-decreasing. It's a non-decreasing sequence. Is a non-decreasing sequence. And b's of k is a non-increasing sequence. So in other words, it either decreases or remains the same. What we get is that L must be less than or equal to b's of k and must be greater than or equal to ace of k. And this is true for every k in the set of natural numbers. Okay. Well, yeah. So this is what we get. Now, why is this true? Once again, this is something that you need to think about, maybe on the number line. So think about this. Let's say this is ace of 1 and this is b's of 1. The one thing we know is ace of 1 is an increasing sequence and it converges to L. So let's say that this is L. Now, since it converges to L and it's an increasing sequence, we know that all that infinitely many different values of the sequence ace of k must lie in this interval. So it must lie, or in fact, all the values of the sequence ace of k must lie in the interval ace of 1 comma l. And similarly, every single value of the sequence b's of k must lie in the interval l comma b's of 1. In other words, the one thing that we know for sure, so this is of course ace of k and this is b's of k, and for every k, this holds for every k, for all k in the set of natural numbers. So the one thing that we know for sure is that for any k in the set of natural numbers, any value of the sequence ace of k will be less than or equal to l, and any value of the sequence b's of k will be greater than or equal to l. The reason why the equality signs are over there is because it's possible. I mean, you can just replace these open brackets with closed brackets, and it can still be, and you can just replace the strictly less than signs with less than or equal to. I'm not exactly sure if ace of k can actually be equal to L. I don't think so, but yeah, I don't think so that it can be equal to L, because if it's equal to L, then essentially what you get is that after a certain point, the the length of the interval ice of k is no longer getting smaller, because when, I mean, if at any point ace of k is equal to L or b's of k is equal to L, what you get is the length of the interval is L minus L, which is 0, and of course the length of the interval can never be smaller than 0. So yeah, but it's probably an irrelevant issue as far as the question is concerned. So, but that's basically the idea. The one thing that we know for sure is that L will be sandwiched between ace of k and b's of k, or which essentially implies that for every k in the set of natural numbers, L lies in the interval ace of k, comma b's of k, which implies that for every k in the set of natural numbers, L lies in the in ice of k, which means that that L is, well, okay, uh, yeah, it should end over here. So what I was gonna do, I mean, this argument should end over here. There's an additional argument to be made. What I was going to write, which would have been incorrect, was that the intersection from k equals 1 to infinity of ice of k is equal to the set containing L. And this is false. This is not true. Or I mean, this is true, but I haven't proven that this is true. And the reason why I haven't proven this is true yet is because what I have proven is that L lies in the intersection, or in this intersection, but I haven't proven that this is the only point that lies in this intersection. So I need to prove that there are no other points that lie in this intersection before I can make this stronger conclusion. But the one thing I've shown, or one thing I can conclude, is uh, what I'm going to say over here. This implies that L lies in all i's of k, right? So L lies in all i's of k. Okay, the next thing, and this is the final argument. Finally, observe that no other point can lie in all sets, in all i's of k. I'll argue by contradiction. So there are two cases to consider. So the first case, case one. In fact, before I lay out the case, what I'm going to say is let assume L prime, which is not equal to L, lies in all i's of k. Now we have three cases, and I'm gonna prove. I have two cases, and I'm gonna prove that both those cases lead to a contradiction. So case number one, L prime is greater than L. So on a number line, and I'm just going to leave this number line over here, if this is L, then L prime is right here. Okay. So this is case number one. Now notice that as the sequence piece of uh, the sequence piece of k converges to L for a k, or I would say I pick a k, I pick a k sufficiently large such that L is less than or equal to piece of k, which is strictly less than L prime. And this is once again always possible to do because the sequence piece of k converges to L as k tends to infinity. So in any neighborhood of of L, there are always points of the sequence piece of k. So it's always possible to find at least one point of the sequence piece of k. In fact, it's possible to find infinitely many such points, but it is possible to find at least one point, a piece of k, that lies in the interval defined by L, that lies in the interval L comma L prime. Then, in fact, instead of k, I'm just going to call this I for now, just to avoid, in fact, not even I, I'm just going to call this J for now. I just want to avoid any confusion. Then, the interval ij, which is equal to the closed interval aj comma bj, does not contain L prime. Thus, we have a contradiction. So that's the first case. Clearly, there can be no L prime that is greater than L because there exists at least one interval in which L prime, which does not contain L prime. So the second case is when L prime is less than L. So I'm just going to draw a number line again. So in this case, let's assume this is L and then this is L prime. And once again, in this case, I mean, if you understood the previous case, then you probably know what's going to happen. Now, instead of using the sequence piece of k, I'll be using the sequence ace of k. So I'm going to say as ace of k tends to L, I pick a, let's say H, pick a H sufficiently large such that L prime is strictly less than ace of H, which is less than or equal to L. Then the interval I of H, which is equal to ace of H, comma piece of H, does not contain L prime. Thus, we have a contradiction. Therefore, the only point in the intersection of all sets is of 1, comma is of 2, comma is of 3, and so on is L. And yeah, that completes the proof. So what we have shown in this theorem, just to give you a quick recap, what we've shown is that as long as we have a bunch of intervals, each one, or in infinitely many intervals, each one contained in some other interval, and that the length of these intervals tend to zero as k approaches infinity, then there is exactly one point, and one point alone, that is contained in all of the intervals. Or in other words, there's exactly one point that lies in the intersection of all these intervals. Yeah, so okay, yeah, I made a tiny mistake. It's not sets, although I mean, saying it's a set is not wrong. I mean, every interval is just a special type of a set, but I'm just, just to be consistent, I'm gonna say all intervals. And the way we prove this is we have to use the monotone convergence theorem. To show that both the sequences a sub k and b sub k, where a sub k is the sequence of lower bounds of the intervals and b sub k is the sequence of the upper bounds of the intervals, that both of these were monotonic and bounded, and thus by the monotone convergence theorem, both of them converged. Then we use the assumption that the length of these intervals tend to zero as k approaches infinity to prove that both these interval or both these sequences a sub k and b sub k must have the same limit. Then we basically used the idea that a sub k was a non-decreasing sequence and b sub k was a non-increasing sequence to show that L was sandwiched between a sub k and b sub k for every k in the set of natural numbers, which essentially allowed us to conclude that L lies in all the intervals I sub k. But we were not done at this point. This is a mistake that a lot of students make, especially in this proof. They believe that, well, you're done at this point. No, you're not done. The only thing that you've shown so far is that L is a point that lies in all the interval size of k, whereas the theorem said that there is only one point that is contained in all the intervals. So you need to show that this is the only point and there are no other points. So in order to prove that there are no other points, we essentially argued by contradiction. We said, assume that there is a number L prime which is not equal to L, which lies in all intervals ik. There are only two possible cases. Either L prime is greater than L or L prime is smaller than L. That's simply because the set of real numbers is an ordered field. So there are only three possible cases. Either L prime is less than, greater than, or equal to L. We've already assumed it's not equal to L, so it must be either greater than or less than L. So, well, in the case if it's, we obtained a contradiction in both cases. We showed that L prime cannot be greater than L and L prime can also not be less than L, and therefore there is no other point L prime that lies in any that lies in the intersection of all sets I of k. And thus we were able to conclude that the only point that lies in the intersection of all the intervals is L, and that completes the proof. And this is the first lemma that I'll be using in subsequent proofs in order to prove the Bolzano-Weierstrass theorem, and then use that theorem to prove a important theorem or an important consequence, or, well, I would say an important corollary of uniform continuity. So yep, I hope you enjoyed the video, and I'll see you in the next video.